Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve a buckling analysis. So we have taken, this is the material property. In buckling analysis, we have four type of end conditions and different types we have, but mainly four types. In that, we are going to do a fixed and free column. This is the case we are going to analyze. So we have taken this one end is fixed and another end is fixed column of length of 1.5 meter and it has breadth and depth both are having 0.1 meter. We have taken Young's modulus and second moment of inertia we have calculated, and this is the first critical load for this case. So 1.91 into 10 power 6. This is the first critical Newton. This is the first critical load for this case. We will solve this problem using salome. So we have got this value 1.91 into 10 power 6. So the first critical load, it will deform like this. We can compare the results. So you see, both will, it is deforming the same way. So the load also we are getting the same value. So now we will solve the problem using salome. Just closing this one. Now we'll open salome. So first go to geometry model. In our case, the length is 1.5 meter and breadth and height both are same 0.1. So we can model this in any axis. Now I'm going to take length unit in z axis. So new entity primitives box. In z axis is 1.5. Remaining are 0.1 and 0.1. Now say OK. So this is the column I have taken. Now we will create groups to apply the boundary conditions. Create group, volume group. I am giving name as beam. Apply. Second, I am going to give name as, here I am going to fix it. So this one is a fix. Apply. Here I am going to apply compressive load. I'm just naming as load. Apply and close. Now we have created this geometry. Now we will save this file. Go to file, save as. So our case is fixed and free buckling. Here I am saving it. Now we have saved this. Then we will create a mesh for this geometry. Go to mesh, create mesh. In this case I am going to use hexa element. So hexahedron. 2D I just want to make quadrangle mapping. In 1D I just want to use wire discretization, local length. So the value I am giving 0.03. Save OK and apply and close. Now this right click this mesh one, go and compute. Now I have created a mesh for my model of 800 hexahedron element. This is a linear element. So in this particular case I am going to use quadratic element to get accurate results. So just close, modification, convert to quadratic, just apply and close. Now we just go to mesh information. Now see, the linear element are converted into quadratic element. Just say OK. Now go to mesh 1, check the groups. This one is fixed, this one is the load, this one is the volume group. In buckling analysis, what we are going to do is, first we are going to do static analysis, then we are going to calculate stiffness for the buckling. So first we'll solve the static analysis using salome. For that we are going to use efficient to create the command file. So I'm just opening efficient wizard analysis. This one is the 3D analysis, leave this one. Material, I'm just giving our material property and assign to beam. Add. This is a beam element, sorry, this is a solid element. We need not to specify this one. Go to boundary condition. So ours are mesh group, just go to mesh group. First one is fixed, assign to fix. So we need to define only translation. Rotations are not required because the solid element doesn't have rotational degree of freedom. These three are enough. Just go to add. The second group we are fixed at the bottom. Now we just want to apply load. So go to load. Here we can choose pressure and force. Both will apply as a pressure only. Only thing is pressure, it has only compressive positive and negative value. If it is a compressive force, compressive pressure, if it is a positive value. If we are giving a negative value, that means tensile pressure. If you are using a force on the face, means it will also apply as a pressure only, but it has a direction. In this case we are going to apply compressive load. Anyway, we can use pressure. I'm just going to use pressure. Assign to the group name is load. You can check here, the group name is load and the value is 1. So whatever the value we are giving, the unit load, so in buckling analysis, whatever it's coming after solving, the load will be multiplying with the value. So 1 is the easy value, for that I'm giving 1. So whatever the value we are getting, we can multiply with that value. Okay, so I'm giving a 1 as a compressive load. So 1, just add it. Go to output, just add all, save the command file. So first we are going to solve static analysis. So I'm going to name as static.comm, save, exit. Now I have created the command file and I have created the mesh. Now we'll export this mesh also. MID format, same location, I exported. Now we'll use ASTK. We'll use the code aster ASTK to solve the static problem. Now choose the location. First one is the command file, next one for mesh file, remaining we can give output file message, error, resu and RMD file. This is the way we just want to put. So first one, so we'll go to the folder for avoiding the error. So by pressing Windows key and left arrow, we'll keep this left side. Same way we can keep this right side. So this one is the command file. The file name is static.comm. The next one is mesh file, mesh_1.med. This thing we can name it ourselves, any name we can give. I'm just giving message.mess, error.err, resu.resu. This is I'm going to name as result_. static dot rmad. So now I have done. We can set the memory how much we want to use. I'm just going to use 2 GB. So 15 minutes is much more time, so I'm just keeping this value. If you want to increase, we can increase this value. So you can see here hour, minute, second, we can change this value by setting it. Now just tick this interactive follow-up. Now we just want to save this setup. Go to file, save. Now astk, any name we can give. I'm just giving simple name. Saved it. Now see this one. Now we can run this one. Go to run. Now we will check this. Now see the result files are generated and static. This is a command file and this one is the message file. We will check this message file if any error comes. Now see, there is no error. The static analysis solved very nicely. Now only thing is we have applied 1 Newton per meter square as a pressure. You can see here we have applied pressure. This value is nothing but 1 Newton per meter square. But in our case we need to apply a force of 1 Newton. For that we need to add a variable force is equal to, so whatever this command, pressure or force on the face, everything, these two command will take as a pressure only. So just make it 1 divided by area. Our area is, just go to geometry. Now we are in the mesh module. Just go to geometry module. Now select the face where you want to apply. So load, go to inspection. There is an option called dimension. Use the bounding box. Instead we can go for inspection, properties, this on the surface unit. Because the load is not a volume unit, this is a surface unit, we can directly specify this is the area value. So 0.01. Anyway, this is a simple object. We know the area of this surface is, so 0.01. So we can specify in that way, or we can go for, we can specify the unit. So I am going to specify 0.01. Done. Now I have specified the variable. This is the value I just want to apply it. So the same variable we just copy and place it here. Just copy and place it here. I have placed here. So now this value will come like 100. So 100 is a pressure is equal to 1 Newton, because this will apply as pressure. So that's why we are converting in this way. So now now this 100 is equal to 1. Now just go to here, just close this one. Now I have modified the static analysis. Now we can run this case. Now it is solved without any error. Now we can see in load it has taken 100. So now we have applied 1 Newton force. 1 Newton force in the top surface as a compressive load, and we are fixing here. Now we'll do mode buckling analysis. So for that, just go here, just close these two values, two command files, go here. Now we'll copy the static.com. Just paste it here, rename it as buckling. Now for buckling analysis we have the command, just this one, the command for buckling analysis. I'm just copying this command, just go to the current buckling just paste it here. Now this is a buckling command. This is the up to this is static command. This one buckling command. First, this is calculating a stress field for geometric stiffness. So whatever we are doing is static analysis. From that it is calculating the stiffness. Then calculating the geometric stiffness matrix. First it's calculating this stress. From that geometric stiffness is calculating. So then it's calculating stiffness matrix. Then it is assembling the matrix. Finally it's calculating. This is the solver part buckling. So we are using calc mode. So it's solver. Then we are saving the results in 81. So we'll do the same one. Now we'll save this buckling one. We'll close the folder file. Now we'll check one by one. First one is up to this we have done. There is no error. Now this first command we need not to change anything. So in second command also we are using model. So the same model we need to check it. So we have used same model. Yes, the file name is same, model. Here also the same. And f sigma we are taking the stress value from here. F sigma, so it's correct. The next command we are using a model, same model. Material, we need to check the material the same way we have specified or not. Material is same, the will keep the same. Then fixed and pressure. So boundary condition we need to include here for calc matter element. For that we just go with the check here. So this one is fixed and this one we are named as load. So for that we need to change this into load. So whatever we need to include the boundary conditions name. Then this is the giving name SMEC. Then these are just assembling the matrix, need not to change anything. So from the static analysis we are included everything. Then finally it's solving from the stiffness matrix from critical load. Then finally it's saving the results for view the results in paraview. So this is a mesh, just check the mesh. Yes, MES only. So then solution. So we are calculating buckling value in solution command. So the same value here used. So now everything is fine. Now we can save this command file. Now we'll close this file. Now go to ASTK. Now add one more one. Just added here. This is also in RMD format. This naming as result underscore buckling dot RMAD. Now you just name it as 81. Now we can save this file. Now I have saved it. So now we'll run the case. So I'm just running the case. So now it is solved. We'll check the message file. Now see it is done only the static analysis because we are not changed the file name. See here we have given only the static. So now we have to use buckling command. So change this into buckling dot com. Now only it will. So now we'll solve this case. Now it's reading this file. So now you can check here. So the result buckling RMD file is generated and we can check the message file. Now see, yes, the static solver is finished up to this. Now the buckling command is started reading and it's calculated a critical load. So it has calculated a 10 number of critical loads because we have specified 10. But we want only the first critical load. So in that only it will start to buckle. the first critical load value is 1.919 e power 6. So we'll check the results in analytical. Now see the analytical value also 1.919 into 10 power 6 Newton. The same value only we are getting in salome. Now we will check the results in which direction is getting bending. We'll close this one and just go to paraview. Just open pictures, code aster, this one. This is the result file for buckling. Just say OK, just apply it. Now we got this file. Now go to displacement and we can change this color. I'm just giving this one green to blue. Just apply it, close it. Now we can check the value here. The first value is 1.919. For that we'll see the deform shape. Go to wrap by vector. So I'm just giving the scale factor of 50%. Just apply it. You see, so this is bending like this. So the second mode also will get the same because it has the same cross sectional area. And the third one, it's bending in that way. Similarly the fourth one is bending in this way. Fifth one, sixth one. This is the way it will deform. Now the first one is enough for us. So this is the way it's getting deformed. So in analytical also we are getting the same value and side of deformation. So in this case we have seen how to solve buckling analysis analytically and using salome. We compare the results. So thank you for watching my videos. Please subscribe my channel for more videos. Thank you.